Welcome back to CHENG 323. Today we're gonna continue the previous example that we have started in lecture 15. So let's start with lecture 16. If you recall, the problem was that we had a reversible reaction and then we had few requirements. The first requirement was to find the equilibrium constant Kc, which we have found in the previous lecture. The second requirement is to calculate the equilibrium conversion Xe of NO in a constant volume batch reactor. So as you have noticed here, the reaction is reversible, so you will not get complete conversion. Therefore, we want to calculate what is the equilibrium conversion. In other words, if I leave the reaction for very long time in the constant volume batch reactor, what would be the achieved conversion? Because if we leave the system for a long time, equilibrium will be reached. Requirement number 3 is to calculate the equilibrium conversion in a flow reactor. And then we have a couple of other requirements as well. Okay, so let's start now with requirement number 2. Calculate equilibrium conversion of NO in a constant volume batch reactor. So the question is, where are we going to find Xe from? Well, Xe is related to thermodynamics because it's an equilibrium conversion, and equilibrium conversion is related to equilibrium constant K, right? And of course K is related to Kc, so let's use Kc then. Kc, what was the definition of Kc? Kc was the definition of Kc is the concentration of the product divided by concentration of the reactant, each raised to the stoichiometric number, correct? And these values has to be at equilibrium. Okay, so Kc equals concentration of C at equilibrium divided by concentration of A at equilibrium divided by concentration of B at equilibrium raised to the power 0.5. Obviously, we have the value of Kc. However, here we don't have these values. So that means we have 3 unknowns, and we cannot solve one problem with 3 unknowns. So we can express the concentration as a function of x for each of these concentrations, and we will end up with one equation with one unknown. So let's start doing so. You know that for a batch system, Ci equals Ni divided by V. And we know that Ni can be expressed as a function of x as follows: Na naught times theta I plus nu I times x divided by V naught, because V is constant, the volume is constant. Upon simplification, we get this equation. And as I explained earlier, please do not memorize this equation. Always start the concentration equation from its basic definitions. Okay, so we want the equilibrium we want the concentration at equilibrium, and we need the concentration of A, B, and C as well. So as you can see, we can write this equation for A. So here we go, Ca at equilibrium equals Ca naught. What is theta A? Obviously theta A is always 1 because it is Na naught divided by Na naught. Then what is nu I for A? It is 1. So here we go, minus x, but because we're dealing with E here at equilibrium, so the X also will be at equilibrium. And we do the same for B, okay, and we do also the same for C. Okay, now we have to evaluate theta B and also theta C. The new were easy to evaluate. Okay, so how do we find the value of theta B? As mentioned earlier, whenever you want to find the value of theta, you look at the feed. So you look at the feed and says the feed consists of NO with a partial pressure of 0.259 atmosphere and 20% excess air. So that means we need to do some calculation regarding to the excess quantities that you have covered in CHENG 111. Here I'm providing you with the answers, so please conduct these calculations by yourself. If you don't remember, please refer to chapter 4 and Fogler textbook of CHENG 111. Basically, if this is the partial pressure of NO, then the theoretical partial pressure of oxygen should be, the theoretical partial pressure of oxygen should be half of this. However, you're not providing a stoichiometric quantity, you're providing 20%. So you take this value, multiply it by half, and then multiply it by 1.2 because you have 20% of excess air. So you get this guy, and then of course oxygen comes along with nitrogen in air. Therefore you want to find the partial pressure of nitrogen as well, which you know how to find it. You multiply this by 0.79 divided by 0.21 and you get the partial pressure of nitrogen. So that's what we have in the feed, A, B, and the inert nitrogen. We don't have anything else, so you can sum all of these guys to find the total pressure at the feed of the feed. Okay, now you can calculate theta B. You can calculate it from number of moles, or you can calculate it from the partial pressures as well. You can calculate it from the mole fraction, whatever you feel comfortable with. Okay, so partial pressure of B divided by partial pressure of A, both at the feed, will give you the value of theta B. If you look at the feed, you do not have C in the feed, so theta C will be 0. And we can also calculate the value of Ca0 using the ideal gas law, which says Ca0 equals Pa0 divided by RT0, and we have the value of temperature here. Okay, so we have the value of Kc, it's given, and we have found all the equations for the concentrations. So let's do this. Let's substitute. So Kc, here we go, this is the value of Kc, and this is the equation for concentration of C, this is the equation for concentration of A, and this is the equation for concentration of B, all at equilibrium. Of course, don't forget to raise the concentration of B to the power 0.5. Okay, let's see, Ca0, we have the value of Ca0, so that means the only unknown is Xe. As you can see, the only unknown is Xe. You can use a solver in your calculator to find the value of Xe, and we find it to be 0.26. So that's the equilibrium conversion, which means if I leave this mixture in a constant volume, batch reactor, and will let the reaction to proceed at temperature of 770 Kelvin, and let it proceed until it reaches equilibrium. The conversion, the achieved conversion, the equilibrium conversion will be 0.26. طيب, now let's discuss how to find the equilibrium conversion in a flow reactor for this given reaction when carried out under these conditions, including the temperature. Okay, so what we mean is, if the flow reactor, for example, a plug flow reactor, was too long or long enough so that equilibrium conversion would be achieved, then what would be that conversion? So let's calculate together this. Of course, the value of Kc will not change. The expression of Kc will not change with the change in the reactor. However, what would change is the concentration expression. So we have a flow reactor, therefore the Ci equals Fi over epsilon. And this is a gas phase reaction. So epsilon equals epsilon naught times the three correction factors, which are the correction factor for the number of moles. Obviously here the number of moles is decreasing. 1.5 moles go to 1 mole. And the correction for temperature. And then finally the correction for the pressure. Okay, let's proceed. Okay, now we have the concentration Ci equals Fi, which equals Fa naught times theta I plus epsilon naught times x divided by epsilon. And we said epsilon equals epsilon naught times these three correction factors. Of course, the total number of moles changing, so this remains. The temperature is constant in this case because we have an isothermal operation. So this guy goes to 1. And let's look at the pressure. Let's assume that there is no pressure drop in the reactor. Therefore, this guy also equals almost 1. So negligible pressure drop. And therefore, the remaining term is epsilon equals epsilon naught times 1 plus epsilon x, which is here. Okay, upon simplification, we see that we end up with this expression. Now we can write this expression for both, for the three involved species, which are A, B, and C. So let's do that. Before we do that, we need to calculate epsilon. And we said epsilon equals delta times Ya naught, or Ya naught times delta. So we need to find Ya naught. Of course, Ya naught equals Pa naught divided by Pt naught, which we found on the previous slides. And here we go. And then epsilon equals Ya naught. This is Ya naught times delta. How do you find delta? Of course, we find it from this equation. 1 minus 1 minus 0.5. So we have minus 0.5. So now this is the value of epsilon. Okay, so there we go. This is the expression after substituting for Cc and Ca and also Cv to the power 0.5. Now you use your solver again to find the value of epsilon x. And this is the value of epsilon x. So this is the equilibrium conversion for this reaction at these conditions when run in a flow reactor. Okay, so let's see. For this reaction at the given conditions, if we use constant volume batch reactor, the equilibrium conversion is 0.26. However, if we use flow system, then the equilibrium conversion will be 0.263. So the question now is, why the equilibrium conversion is slightly smaller when we run this reaction in a constant volume batch reactor? Of course, to answer this question, you will need Le Chatelier principle. So I'll leave you with this to think about the situation and the answer. Okay, let's go to requirement number 4. Assuming the reaction follows an elementary rate law, express the rate of reaction solely as a function of conversion for a flow system and for a constant volume batch reactor. Obviously, the first thing you need to do is to write the rate law. Reaction follows an elementary rate law, very simple to write. So you look at the reaction, and then based on that you can write the rate law, where the powers, all the powers are identical to the stoichiometric number. Okay, now what? Now of course you'll need to substitute for the concentrations with the respective equations. Ca, Cb, Cc as a function of x for both systems. For flow system, here where the volumetric flow rate is variable, and for constant volume batch reactor where obviously the volume is constant. Okay, so we either use this or this, and here's the answer. Last requirement, determine the CSTR volume necessary to achieve 80% of the equilibrium conversion. Assume K equals this much and if A naught equals this much. That's really an easy task. Okay, so what is the desired conversion? How much conversion you want to achieve in the CSTR? Basically, you need 80% of XE of the equilibrium conversion. So which equilibrium conversion you will use? The 0.263 or the 0.260? Obviously, you're going to use that for flow system. Here we go. Xe equals 0.263. Okay, and of course, CSTR is a flow system. Remember that. Okay. And of course, we are asking ourselves, do we have a variable volumetric flow rate system or constant volumetric flow rate? So we don't ask if we have a constant volume system or not, because we're talking about flow system, and what affects the concentration is the volumetric flow rate, not the volume. Okay, so flow system, we know what Xe is, and we know that we should take into account that the volumetric flow rate is not constant. So what's the conversion? The desired conversion is 80% of this guy. So that means 80% times this guy will be 21%. So the desired conversion is 21%. And the rate law, we just wrote the rate law for a continuous flow system as a function of x. So basically you can substitute x with 0.21 to find the value of minus RA, and we have the design equation for a CSTR. If A naught is known, minus RA is just evaluated, and x is 0.21, and here we go. The answer is around 500 liter. Okay, so this is the area representing the volume of a CSTR, and remember the conversion, equilibrium conversion was 0.263. Here we go, 0.263. Obviously, if you want to achieve equilibrium conversion, you should use infinite volume for the reactor. Okay, there are lots of slides at the end of chapter 3 handout, and please go through them so you would learn yourself more. Okay, to conclude, so we learned how to write mole balances in chapter 1, and we learned how to write rate laws in chapter 3, obviously, and also chapter 3 part 2 we learned how to utilize the stoichiometry, and we build the reactor design blocks one on top of the other, and this is how you design a reactor. Okay, with this we come to the end of chapter 3. Please make sure that you solve all the suggested problem and set number 4. Wishing you all the best, and we'll meet again for the lectures of chapter 4. Bye for now.